Hello. Okay, good afternoon, everyone. Can you hear me?
Yes, we can.
Yeah.
Okay, so I just got a confirmation that I should start the session. So let me just begin with the introduction to Cox regression analysis. So let me just share. Yeah, it's already shared my screen. So, okay. All right. Okay. I hope you are able to see my screen.
Yes.
All right. Now, see, Cox regression analysis as such has it's from a family of regression analysis, but its origin is basically from exponential distribution. Okay. Now, where does this Cox regression analysis come into place? When we talk about longitudinal studies, wherein we have a focus on a particular event. Okay. So, like for instance, in marketing, it would be about a person leaving an organization, sorry, leaving the services of a particular company. Okay. Or it could be even from the employee perspective, our employee leaving the organization in the HR, right? Or in healthcare, it would be more about any terminal illness where somebody will reach the death stage, right? So there is an event which we are talking about here as our focus. And why it's a longitudinal study? Because over a period of time, you would be expecting somebody to leave the organization, or somebody to leave the services, or somebody to reach the dead state, right? So there is a state which comes into picture, and there is a time taken to reach that state. Okay, so that's where the analysis, what we call as survival analysis, is the family of these particular techniques. So basically, Cox regression analysis has something to do with survival analysis, as well as because it's a form of a regression equation. That's why it's also called as Cox regression analysis. Okay. Now, I had a case study which I have shared with you. Okay, so I'm just trying to get directly into the application. And since this particular session was meant for the postgraduate students of health economics, okay, from that perspective, I have taken up this case. Okay, now in this case, there is a research going on for a cancer treatment. Okay, so they found out there is a drug, or you can say the series of treatments called anti-cancer. Okay, now to test this on those who are already suffering from cancer, right? So a test was done. Obviously, here all the agreement with the people who undergo the test would be taken up, right? So all that ethical guidelines would be followed, right? But however, here we like to check that whether there is some positive effect of a treatment over the illness. Okay, so obviously there would be a control group and there would be a treatment group, right? So the treatment group where they would be undergoing the treatment as per anti-cancera, okay, and those who do not undergo treatment at all. Okay, now here we define a state called the death stage, or a state where the person won't survive. Okay, right? So keeping that in mind, so let me just okay. We talk about what we call as the survival time. Okay, so survival time now so there would be in this longitudinal study, there would be a period in which this study would be based, say for 6 months. Okay, depending upon the intricacies of the treatment. Like here, it possibly would be about around 5 to 6 months. Now, during this period, if the person who is undergoing the treatment, okay, doesn't survive, that means that particular state has been reached. So we generally say that as the survival status, which is equal to 1. Okay, so it would be a binary state where we'll say that either the person has reached that particular event. Okay, so the event which when it's reached is called as status equal to 1, and if they do not undergo that particular state or they do not reach that state, then it is the status would be 0, confined to that study period. Now, we also need to understand that there could be some people who might leave the process within this study period, or there would be some people who do not reach that state after the study period. Okay, now this is what we call as censoring. That means we do not have any information about those people who have either left the treatment process during the study period, or they would not have reached the state of death during the study period. Okay. Now here, the idea comes from what we call as the exponential distribution. So let me just move to that particular zone. Now, when we talk about exponential distribution, okay, we are talking about a survival function, okay, where we say that somebody would be living for at least this much months or time, right? So that's where we state our survival function as S of t, where t is the time, right? And S of t means it says survival. That means we're trying to see what is the distribution of a particular person who undergoes a treatment, okay, reaching, or what is the idea is to find out the probability whether the person would be sustaining themselves after a certain period t. Okay, so that's where this exponential distribution Can we replace Cox? No. See, logistic regression is basically where we talk about the dependent variable being categorical, right? So it cannot be replaced by logistic regression. This has a different place where we have actually two dependent variables. Unlike any other regression equation, okay, we do not have. Yeah, that's why I am saying that here there are two different variables. One, there is a time, and another is what we call as the status. Okay. Now, status is 0 and 1. So unlike what we generally talk about churn prediction or survival in terms of logistic regression model, where we have only the states, but we do not exactly know at what stage they would exit, or they would churn or they would not churn. Okay, so there is a time period which we are talking about in this. So it's a longitudinal study where there is an event in focus. So that's why we cannot say that this can be simply modeled as logistic regression, because here in logistic regression, we do not have the time factor into place, right? So whereas here we are trying to see whether the person is able to survive. Like now here you can understand survive either in the organization, right? So when the person churns, yeah, so time is also a dependent variable. Yeah, you are right. So time as well as the state, both are dependent variables. Okay, so that means you try to understand when the churn or when the person dies happens, right? So you can take it in any context, whether if so churn, death, okay, or leaving the services mean the same here. Okay. So when we talk about time, we have to get to a distribution which will explain what is the likelihood of a person reaching that particular time before reaching the state. Okay. So when we say e to the power of minus lambda t as the exponential function, okay, it basically means that is this t is the minimum time they might have to reach, and what is the likelihood of that. Okay, so that's how the distribution of survival function works. Okay, in contrast to that, we also talk about this. Now in this part there's something called this lambda. Now this lambda we generally assume in exponential distribution as a constant hazard rate. Okay, that means it is the rate at which any particular entity will decline. Decline in the sense, like generally we use exponential distribution for even bulbs or any type of electronic instruments. So we want to know what is the average lifetime of such devices, right? So in the same sense here, when we talk about this lambda, it talks about the rate at which there would be a decline. Okay. Now that's what we also look here as our hazard function. Okay. So hazard function basically means the other way around of it. So understanding that till what time the person might survive, or till what time the person might continue to stay in the organization, and so on, right? So that's what hazard function means. Okay. Now, taking cue from this exponential distribution. Now, say exponential distribution is basically taking into consideration that no other thing affects the decline, right? Like we only understand it as a function of time. Okay. Whereas if you want to introduced that there could be some factors, external factors, which might induce in the degradation of a particular entity, right? Or it could be even upgradation, because when we talk about survival, it would be the other way around, that are we trying to increase the chances of survival, okay? Or it could be about factors which might result in the decrease of a survival, okay? So those things which are not time bound, but at the same time they are affecting the state. Now those things can be only incorporated in this Cox regression model, okay? So though there is you can say that it's an extension of exponential distribution, okay? But wherein there is some covariates or independent variables other than which other than the time only. That means there's saying it in exponential distribution, there's nothing called because it's basically we are talking about probability, right? So probability of a particular entity staying for some time or leaving for some time, right? Whereas in Cox regression model, we are trying to see what are the factors which will make the person leave for certain time, okay? So that's where the exponential distribution has some role to play here. But at the same time, there is an add-on of regression aspect in the Cox regression model. Now, that's where now I introduce you to certain parameters and also some of the outputs which you would be looking at. Okay, so if you look at the hazard function which I described earlier, it was only simply lambda, right? Which was a constant rate at which the events might occur. Okay. Whereas when it comes to the hazard function here, we say that there is a covariate x, that is the set of factors which might affect, okay? And we are introducing their beta values, okay? And then modeling the hazard function. Okay.
Yeah. Can I ask a question here?
Yes, please.
Yeah. So if I understand it right, you are sort of looking at an exponential distribution where the average sort of varies with some x. Is that understanding right?
Yes, exactly.
Okay. Yeah. Okay. Thank you.
Yeah. So you can understand that the exponential distribution is a special case in that sense.
Yes.
Because
Yes. Yeah, I got that. Yeah. Then this is a more generalized version. Yeah, I got that. Yeah. So which means like if it is not dependent on x, then it becomes an exponential distribution.
correct. Exactly.
Right. And also, so just one more question. So does this have anything to do with this increasing failure rates in distributions? Is that related to this? So there is, I remember reading something on IGFR and IFR in distributions.
Yes, see, this when it comes to failure rates, the failure rates, it's basically a hazard rate only.
Okay. Yeah. Okay.
The failure rate
Yeah.
itself is a hazard rate.
Yeah. Okay. Yeah. Okay.
Yeah.
Yeah. Thank you. Yeah.
Yeah. So just to give you a formal definition, it's about a measure used in survival analysis to describe the relationship between the survival times of different groups within a study. Now, here, see, generally what happens in survival analysis is it is best understood when it is done in comparison with something else. Okay. For instance, Like if we are looking for the efficacy of a particular drug, by itself, you may not be able to figure out whether that the drug is no good enough. Okay, so you need to compare it with something else. Okay, so most often what happens is that whenever you are doing a survival analysis, it never about one particular uh, group or something like that, but rather it would be more about comparison. Okay, that's why we always have what we call as the hazard ratio. Okay, so hazard ratio itself suggests that there would be some type of a comparison. Okay, with respect to something else. It's a geometric comparison which we would be doing up. Okay, that means we would see that what is the hazard situation for one particular treatment over the other treatments. Okay, now in our particular model which we have used here, we only have a treatment group as our covariate. Okay, so that means it's just only trying to, so treatment group is basically here a binary variable, as you can see even in the data set which I have shared with you. Okay, so it's a binary variable where it just suggesting that somebody who is undergoing treatment is treated as 1, like the state the group treatment group is equal to 1, otherwise it would be equal to 0. Okay, so under that circumstance, a hazard ratio would be something where we are trying to see what is the hazard, or what is the decrease in hazard basically. Okay, is the hazard related with treatment geometrically more than the hazard related to non-treatment? Okay, that means are we see overall when we have to check the efficacy of the treatment, we would need to see whether the treatment has reduced the risk, okay, rather than increasing the risk. So naturally what we expect is that if the hazard rate of treatment divided by the hazard rate of non-treatment should be less than 1.
But
Okay.
sir, it can happen that in control or in an experimental group, the
Mm.
number of participants in any case, they are reducing in number. Maybe we are not getting it, maybe they have died or something like that has happened. So because this is a longitudinal study, in experimental group or maybe in control group, the data samples are not balanced. In such situation, what will happen? The hazard ratio will be a biased one, right?
No, yeah. So in Cox regression, that part is actually taken care. See, just like in logistic regression, there are different ways of doing the regression. So that means there is something called as what is that? Penalty-based regression. So penalty-based regression generally tries to avoid that overfitting of the model. Okay, so talking about the same situation of biasness, when there might be more number of people undergoing treatment and say less number of people are uh, not not undergoing treatment. Now, even in such cases, if you want to see whether the treatment is effective enough, we generally tend to do, or rather in terms of unbalanced sample, we generally tend to do this type of penalty-based regression. Okay, so in Cox proportional hazards model, also we can do the penalty-based regression. So to avoid getting a biasness based on this.
Okay.
So Yeah, so that is there. So that provision is there. I can show you that in orange. That provision is there. So I'll be showing it shortly. Okay. So in general, we say that if the HR, okay, here HR is the hazard ratio. So a hazard ratio is greater than 1. It indicates an increased risk of event, okay, for the treatment group compared to the control group. So that means that there is a some side effect of that treatment possibly, which has led to the uh, unexpected consequence. If HR is less than 1, that is what is our expectation. Okay, so indicates a decreased risk of the event for the treatment group compared to the control group. And of course, if HR is equal to 1, then it means that there is no significant effect of the treatment, right? So that means it's not good enough as a treatment, right? So yeah, so let me now show you some of the, before we discuss this. So let me just go to the data. Now in several softwares, some of the survival analysis components would be definitely there. So I'm just going to share some of the ideas. So let me first do it in R. So in R, we have this package called survival. Okay, so survival package has to be installed. So obviously you should read the data, and the function for Cox proportional hazard function model is this Cox PH. So notice that uh, we have a survival based object. Now survival based object basically means that it will have in its form two parts. One is the time, another is the status. Status basically or usually would be a binary variable indicating that either you reach that particular state or not. Okay, so status combined with time, that would be the combination of dependent variable. Okay, whereas if you see in the independent variable side, that would be the treatment group. Okay, so and that's it. So this is more or less like a regression equation, right, where you have a dependent variable which is a combination of time and status. And whereas in the independent variable, you have only the treatment group. So I've just taken a very simple example to start with. So, so to understand this clearly, right? So treatment group is again a binary variable, which I said that either if treatment group is 1, that means they are undergoing that treatment. Otherwise, they are not undergoing that treatment. Okay. So usually the minimum requirement for having a Cox proportion hazard analysis, it would be that you need to have the time till which they would be surviving or spending in the study period, okay, and the status, okay. Right. So that's how this model would be designed, right? And then let me just show you the results. Okay. So the result here again is similar to the regression equation. So here we have only the one independent variable called treatment group. So there is a coefficient associated with that. Okay. But what we are interested is in this EXP coefficient. EXP coefficient is basically the hazard ratio, right? So the hazard ratio e to the power of that beta, that would be our coefficient. Okay, so it is 0.3000. Now this one 0.3000 is less than 1. Okay, indicating that those who are now treatment group, when you see treatment group like this, it basically means that it is a dummy variable or a binary variable which has value 1. Okay, so you have to understand that way. So when we say this is treatment group as a variable, so since it is a binary variable, so only that variable which has been flagged to 1, that particular record which has been flagged to 1, for those this is the record which has been shown. Okay, so that means that 0.3000 is suggesting that the hazard risk associated with those who are undergoing treatment is 0.3. Okay, so suggesting that the hazard risk has reduced, okay, compared to those who are not undergoing treatment. Okay, so and of course whether it is significant or not statistically, so that is found out by the p-value. Okay, and the sign itself also indicates that there is a negative effect, right? So the coefficient itself says minus 1.2040. So it's saying that there is a negative effect on the survival time. Okay, that means so the risk is reduced and it is just moving ahead. That means the likely chance of the people who survive would be more. Okay. Now,
So, sir, does it mean minus 1.20? Can we say like this? 20% more chances are there to survive in the treatment group as compared to the control group?
yes. Yes. The risk has, see, the risk actually, strictly speaking, you have to look at from this hazard ratio point of view. Okay. So the risk has been reduced to 0.3. Clear?
Yeah. So from what number has it reduced to 0.3? How do we see that?
See, it's a comparison because, as I said here, yeah. So the hazard rate of 0.3, hazard ratio of 0.3 suggests that the risk of event occurring in the treatment group is 70% lower than in the control group.
Oh, okay. Yeah. So it's not okay. It's not that the rate is 0.3. It is the reduction, which is
Yeah, it's a reduction.
Okay.
See, this is what I suggested, right? So if I
Yeah. Okay.
Yeah, the other way to understand is by interpreting the confidence interval of the hazard ratio. Okay, as we saw there also, that if the confidence interval doesn't include 1, it means that there is a reduction in the hazard. So reinforcing the significant efficacy of the treatment. But if the confidence interval included 1, then that, see, where the value 1, if it's included in the interval. So if you look at this interval, so it's ranging from 0.2167 to 0.4152. So it doesn't include 1. 5% confidence interval on both sides. Okay, so 95% confidence interval. So it doesn't include the lower up and upper limit range, doesn't include 1. So it is suggesting that it's another way of suggesting the p-value is very small. Okay, and the 1 is not included inside this, suggesting that there is a striking difference between the treatment group and the non-treatment group, right? Okay, so that is what the confidence interval of HR means. Okay. Now, can we also visualize this, right? So that's where of course, this is not really the part of Cox regression model, but certainly we can make use of it from the diagrammatic perspective of survival analysis, called the Kaplan-Meier plot. Now, if you see in the Kaplan-Meier plot, the blue color one is the one who have not undergone treatment. Okay. And the red is the one where they are undergoing treatment. Okay. So you can clearly see that there is a steep drop. Okay. In the survival probability, as you can see, the y-axis is survival probability, and this is the survival time. Okay. So this itself is also suggesting visually that the people who are undergoing treatment, okay, they are having more chances of survival. Correct. So if you can look at this survival probability and survival time, that suggests that. Yeah. Now this is a plot coming from orange. So let me just show you orange. Okay, I think 1 minute. So meanwhile it opens. Actually, I had kept it open and something happened. All right. Okay, in orange, it's available as a add-on. Now, now some of you who do not have idea about what is orange. Orange is basically a data mining software. Okay, wherein you can carry out different types of analysis, different types of data processing. Okay, and it also does some of the analysis techniques. So very good for machine learning and predictive analytics. Okay, so there is a additional package. That's why it's getting installed in Orange, which you need to install for survival analysis. And under that survival analysis group, that you would be having this. Okay. Let me just restart this. It's not started. Just a minute. Yeah. So, so there are various softwares through which you can run this Cox regression analysis. Okay. So So the main idea about what to analyze or what type of output which you have to look at. Hopefully it has opened and installed. Not yet. So see, in the options, you will be having that. So survival analysis, you just check this and install it. Okay, meanwhile, it does get installed. Let me show you in JASP. Now, JASP is another statistical software where you can carry out, again, it's a free software, statistical software, where you can carry out different types of analysis. I think in the latest version, they have a zone for survival analysis. Okay, so you can actually get that from the bucket, the additional add-ons. So you have just checked that and it will come up, right? So in survival analysis, you can go to non-parametric. Yeah, so now you can see here that there is a treatment group, which I'll place it in the factors. Whereas my survival time, I'll keep it in time to event. And the status would be in the event status. And what is the event indicator? So it is a binary variable, so it would be 1 and 0, right? And you can show the survival curve plot. So exactly the one which you just saw that. So the exact same survival probability against time. So you would be getting that here. Right, so it is showing you that the one which is on the top, you have higher probabilities of survival, whereas the one which doesn't undergo, the group which has not undergone treatment, they have lower chances.
Can I have multi categories, more than 2?
More than 2, yes, it's possible. In fact, here I have just kept the treatment group. This is a very simplistic example, but you can have multiple variables and multiple groups in under that variables. It's possible. Of course, then the survival plot would be not that easy to understand.
Mm-hmm.
It is possible to have.
Sir, if one variable suppose have 4 categories,
correct,
then one category will be treated as a the baseline group or the control group.
Exactly.
So which one it will take? So
that is generally taken by default one of the groups, just like in
just like
our one of them is taken as a base. See, like when it comes to dummy variable creation, generally what happens is
like one hot encoding kind.
Yeah.
Okay, got it. So any variable will be taken as a baseline and then the rest will be compared against it. Okay, got
correct. Okay. I hope that is installed by now. Yes.
I'm sorry, I'm asking this because I couldn't go through the case and the data. So essentially, if you can describe the data here, it's like we have data on survival time and whether that object has received treatment or not.
Correct.
This is the data that we have, right?
Yes.
Okay. So treatment is 1 and no treatment is 0.
Yes. Treatment group equal to 0 means no treatment. Treatment group equal to 1 means they have taken up the treatment.
Okay. Yeah. Okay. Thank you.
Okay. Yeah, I think pretty much I've covered the highlight. Okay. I think some things are there. So this is the plot as I showed you. Yeah, so these are okay. Now this just let me explain what this means. Uh, See, there were 200 participants. Like in this, the sample size was totally 200. 100 were in the control group and 100 were on the treatment group. Okay. Now, what does this 176 mean? 176 events were observed, indicating a high event rate, which suggests most participants reach the endpoint within the study duration. So it is saying that uh, uh, the people have reached that state. That means people have died after even having treatment. Okay. But now what we are interested in finding out is how these events have been positioned with respect to those who have undergone treatment and those who have not undergone treatment. Okay. That means all among these 200 participants. Okay, please let me just first admit this, that this is a created data set. So it's not a real data set. Okay, so I've just simulated an environment and then I've got this data set, right? Okay. So now, most often what happens is that you do not, sometimes you may find many, if your study period is short, right? Then there is likely chance that you may not observe many events, right? For instance, let's say we want to study how many people will leave an organization within the next 2 months, right? Now, within next 2 months, probably that events may not happen at all, right? So you may have to have a very longer period depending upon the type of study you're doing. Okay.
Do we have something like a zero inflated framework for this? So like in Poisson distributions, there is this zero inflated Poisson distributions to use to study rare events. So if the time frame that we are looking at is small and the events are not going to happen within that time frame,
Hmm.
we can possibly look at something like a zero inflated
I
distribution.
actually I don't have an idea about that, right? Sorry.
Okay, okay.
Uh,
No, no. So I think, I mean, I just thought this will be a good context for that.
okay, okay.
Like if you're, because I know it is there for Poisson. So there is something called a zero inflated Poisson where so Poisson distribution essentially shows the probability of an event occurring, right? Now, if you apply that for, say, earthquakes, within a time period of, say, 6 months, right? So it is less likely that you might be observing that event because it's a rare event. So
No,
there is a separate screen. Yeah.
but one thing what you understand is here in this context, Poisson will not be applicable. It's
No, no, no.
actually the other way
No,
around.
I'm not. Yeah, yeah, I understand.
It's a
This I
mirror
understand.
image, right? It's a because
Yeah.
it's a you know that exponential distribution is a mirror image of Poisson.
Correct, correct. The time,
Right?
if I calculate the time between the events, it will typically follow exponential.
Yeah,
No, so I was hoping that when you said, the events might not occur within shorter time periods.
yeah. So it's
Uh,
not really
yeah.
meant for a very short. See, that depends upon a case actually. It really depends upon in which area you are applying this Cox regression.
Okay.
Okay, so
Okay.
like for instance, the same situation about a person leaving an organization should be if the study period is somewhere say in the month of February and April, then there is a possibility of having a lot of events.
Correct, correct, correct. Yeah, yeah.
Right. So so it's usually that is the case here. So
Okay.
So I just wanted to explain what is 176 events observed. So here basically means they have undergone death in this
Okay.
case.
Yeah. Yeah.
Okay. Yeah, just to explain this that so the minus sign indicates that it is reduced hazard in the treatment group. Okay. And whereas 0.300 means 70% lower than the control group, which I've put forward. Okay. Z score basically means again it's just the uh, uh, ratio of the coefficient and standard error. Okay. Yeah, this is also explained. Okay, now this part, model fit and diagnostic statistics. Now this is like more about how we understand R square things, right? So concordance is more like similar to, I can say, uh, a R square or pseudo R square, you can say, because here we are talking about predictive accuracy of the model. So 0.639, it is suggesting that it's a moderate predictive accuracy. Okay. And these are some of the tests, again, confirming the same idea. Likelihood ratio test, wall test, score log rank test. They are all suggesting different diagnostic statistics to suggest how good is your model. Okay. So more often you can just have a look at one of the tests that should be good enough. Okay. Even the confidence interval will also tell you that idea about from the hazard ratio perspective. If it doesn't include one, it means that that particular variable has been significant, right? Okay. Right. So I'm just talking from the case perspective. So there, based on that case idea, you could say that because there was a statistical significance and there was a low hazard ratio associated with the treatment, so they could consider that treatment to be highly effective. Okay, and they could utilize that in the clinical practice. Okay. And there's some problem with my. I was just trying this orange pencil funny. So it has undergone some error. Okay. All right. So you have any questions? I can take up. I was thinking of showing you the orange platform again, but there's some problem. Yes. Do you have any questions I can take up? Hello. Hello.
Yes, so we can hear
Yes,
you.
sir. You're audible. Yeah, we can hear you. You're audible. Yeah.
Oh, okay. So I'm done with the presentation. So if you have any questions. Yeah, Professor Andrea had some problem with her mic, and so that's the reason she told me to continue. Is any questions from the students? Yes. I guess then we are done for the day. Thank you very much for the active participation.
Thank you, Professor. Very informative session.
Thank you, sir. Same here.
Okay. Thank you.